Let's do two very closely related, simple, basic trigonometry problems. I want to capitalize on the fact that we've done some problems with 30, 60, 90s and just show how incredibly similar it is. It's just that we're not going to memorize the particular ratios in any cases except the special triangles that we've already done. So this would have been a problem in 8-2. A 12-foot ladder leans against a vertical wall, making an angle of 60 degrees to the ground, like in a figure. Two questions. How high, two parts. How high on the wall does it reach? That's going to be GE. And how far from the base of the wall is the foot of the ladder? That's FE. Okay. And the key is that we know the ratios in a 30, 60, 90 triangle. We know that EG over FG, and I'm going to start using the language of trigonometry. That's that opposite side over the hypotenuse. And we know in a 30, 60, 90 triangle, when it's that long side opposite the big angle, that ratio is √3 over 2. Okay, but we know what the hypotenuse is, so we can just plug that in. EG over 12 is √3 over 2. Okay, and then we just solve by multiplying by 12, and we get 6√3. Now, in this case, we might want to leave it exact because that's actually a fairly pretty answer, but I can also have the computer evaluate it numerically for me, and that's about 10.4. And of course, that's feet. Okay. In an applied problem, we're more likely to want a decimal answer. Okay. So let me just add one thing to that. That opposite over hypotenuse, we're now going to say, another way to say that is, remember, opposite over hypotenuse is the sine. And so we're going to say what we really just used is a memorized value of sine of 60 degrees. And we're using the fact that once we know the sine of some particular angle that appears in a triangle, we know that number, then we can put it in and say, oh, that's by definition, it's equal to a side ratio in a right triangle, and then we can solve that pretty easily. Okay, very similar. How far from the wall is the base of the ladder? I'm actually going to copy this and just show you how similar it is. So now that's FE over FG. That's adjacent over hypotenuse. And we happen to know that that's 1/2 because of the beautiful fact that that's half of a equilateral triangle. And now we're going to just have a new terminology for that that's going to be much more general. That's cosine of 60 degrees. Okay, so FE over 12 is 1/2. And so FE is just 6. And that's exact, 6 feet. So a fancy way of saying what we were doing in A2 is we were memorizing things like sine, cosine, and tangent of 60 degrees, 30 degrees, and 45 degrees. And we're going to think about it in those terms from now on. And then we can use those ratios, given that this is a particular 30, 60, 90 degree triangle with one side being known. So if you have a right triangle, you know one angle apart from the right angle and one side, then we're going to be able to find out the other side. So what's the new stuff? I really wanted to highlight that how similar it is. So I'm going to go back up. I'm going to copy this. And the one thing we aren't going to have is that memorized version. Okay, so let's see what the problem is. Identical problem, except I've changed the angle to 52 degrees. That's all. Okay, so how high does it reach? That's about the opposite over hypotenuse. And we just don't know off the top of our heads, and I'm not going to make you memorize like hundreds of different trig values. We just call that the sine of 52 degrees. So far, that's really just a name for that. Okay, so we don't know that quite yet, and we can't quite solve it yet, of course. But the great thing is, you want to imagine that 317 years ago, somebody built an incredibly precise 52, 38, 90 triangle and measured it really carefully. There are much more interesting and advanced mathematical ways that this can be calculated that you'll learn eventually, usually. But you can just imagine that somebody made that real big triangle and that this computer program is loaded with that information that was actually obtained by geometric measurement. Let's do it to 3 decimal places because this is not exactly rocket science here. Sorry, I'm going all over the place. And so I'm just going to put that in. And now it's exactly like the previous problem. We're just going to get 12 times that ratio. It's a little bit of a weirder ratio, but then again, root 3 over 2 wasn't totally unweird either. And I'll compute it. And it's about probably round it to 9.5 feet. Okay. Notice that's a little less than 10.4. We reduced that angle. We made it less steep. So a nice reality check is that should get a little less high. So the new GE is just a little bit less than it was. Very similar. I guess I'll copy this one. It's easiest. How far from the base of the wall is the foot of the ladder? This is now, again, this is FE. Let me just change those all at the same time. Okay, that's adjacent over hypotenuse. That's called the cosine. And if we had no clue what that cosine was, we would be stuck. But we rely on those ancient triangle measurers from hundreds of years ago, or fancy computer stuff. And we say, okay, that's 0.616, let's say round it. We plug in the known side, and we multiply by 12, 7.4. So this length here is 7.4 feet. Of course, a really good double check would be, let's do Pythagoras. And there's a profound, very, very important thing about trig is that the most basic thing about right triangles is Pythagoras, really. What is that? Oh, right, square root that thing. And I should get something close to 12. Looks like I should. Of course, I'm not getting 12 exactly because I rounded. But at least it's a good check that these are plausible numbers.